Chapter 5, Section 4.3 and 4.4, Part 3's video. We're going to continue looking at properties of logs and everything. It says evaluate each expression, which, if any, are equal. So we can look at this and basically, if we're going to look at the ones that are equal first, okay? So these are two things being multiplied, so log of 2 of 64 plus log of 2 of 32. Well, that's the same as C down there. Okay, now we're going to show you how to do this on a calculator. And you can do it by what is called a change of base. Okay, now my calculator will allow me to do log base 2 of 64, and I'll kind of show you that. But I'll do one of them with change base, one of them with my calculator stuff, because some of you may have an 84 that's got this, and I want you to be able to use it. But change of base formula says the log base b of a is nothing more than the log of a over the log of b. So the change of base is how you can evaluate a log if it's doing a base that's not a common log, or base 10 that's on your calculator. Okay, so we're going to go ahead and we're going to say A and C are both equal, right? But we're going to do this, and so we'll do the first one. So it'd be the log of 64 times 32 over the log of 2. Okay, and we're going to get a number, and we're going to put that in. So second mode, clear here. 64 times 32 and 2. So log of 64 times 32 divided by the log of 2, make sure you close in parentheses, is equal to 11. Okay, so we're going to do that, and we're going to put that there, and there you go, it's 11. Now, I'll show you how to do this one. Log of 2 is 64 times, what is it, log of 2 is 32. Okay, so if I go math, arrow up, I can use, on mine, it's called log base. You may not have this if you have an 83 or an 84 with an old program. But if you got an 84 that is updated or everything, you've got this functionality. So we're going to use it, right? So 2 of 64. I'm pretty sure. Yeah, all right. Times, we'll go math, 2 of 32. And arrow out and hit enter. That becomes 30. All right, now we're going to do the last one, and we can do that on the change of base. That's fine, and you could do it on your calculator as well. So I put the log of 64 over the log of 2 plus log of 32 over the log of 2. All right, so that's how I'm going to do it. I'm going to do it by the change of base. The last one, you can do it by, if you got a 84 that's got the log base in the math thing, and then use it. Okay. All right. So log of 64 divided by log of 2. All right. And we'll go ahead and hit enter. Plus, that way I can do what I've got to do. Log 32 divided by log 2. and it'll take care of this division before to add it. So hit that, and I get 11. So I have evaluated it, and it shows that A and C are equivalent, and I've given what it equals. Okay, so that's kind of how you got to do that. You can definitely do it by the calculator, just hitting the math and going to the log base functionality on A. All right, so let's go to the next thing. Compounding interest. So we're going to look at this, and we're going to really look at it, the effects of compounding, right? Which is how many times your interest that's sitting out in a little pocket or bucket is being added back to your principal to make more money. That's basically what you got compounding. How many times is that interest being put back on the principal to make it grow faster and earn more money? So that's the A equals P times 1 plus R over N times N raised to the NT. So suppose you invest $1,000. Well, that's the P at 12% interest. Okay, so the R is 12%, but ladies and gentlemen, that needs to be as a decimal for 5 years. And T equals 5. Time is always in years, never in months, always in years. So if you get something that's mixed up like years and 3 months, you got to convert everything back to a year. Okay. Now, suppose we, and it's already got it here, write a function of n. So it would be 1,000 times 1 plus 0.12 over n raised to the 5n. Okay, so what we're going to do is we're going to look at this $1,000 that we're putting in at 12% interest for 5 years, and we're going to look at the effects of compounding, like 1, 2, 4. I think it's got 1, 2, 4, 12, 52, and 3, 7, 65, right? Annually, biannually. No, not biannually. Sorry, semi-annual, which is twice. 2, and then 4 is quarterly, monthly. So those are the words that go with it. So what we're going to do is we're going to clear this out, and we're going to clear this out. We're going to look at y equals, and we're going to say, okay, we've got $1,000. We're going to type this in right here. This equation is going to go in. Okay, so we got $1,000 that we're putting in. 1 plus 0.12 divided by x, close my parentheses, and then raised to the 5x. So the x is going to represent my n, the number of compounding. So let's kind of go back over to table set, and we got it asking, so that's going to allow us to do some things. Hit delete. Let's go up. Delete. All right, so we need to look at this in annually. We get $1,762 out. If we done it semi-annually, $1,790. Quarterly would be 4. Monthly would be 12. Let's see what else. 52 is weekly, and then 365. So 52 and then 365. So what happens to our amount that we're getting back? Well, it's increasing. It went from $1,762 to $1,821. Almost about a net of about $60+, right? That's pretty good. So the more times you compound it, the more times you're taking interest, putting it back on top of the principal so it can add more money or make more money. The principal grows, right? The more you got in there, the more interest it makes off of it, right? So that's the first part. So that would be what goes in here. Now, what is A? What happens to A as N increases? Well, we just said, hey, the amount increases, right? Now, let's look at this. What value of N is necessary to produce an amount greater than 1818, right? And then we'll go 1820 and then 1822. So those are two things. And we're going to graph it. And it says, so I'm going to set my first thing up. And we've got it. Then we'll go 18, 18, right? And then I need to look at some window limits. They say 0 to 1750, no, 0 to 52. Okay, so let's look at X-Men 0 to 52. Window 0, enter, 52, enter. Let's do it by 4. Let's just step them by 4, right? Every little tick mark's 4. Let's look at our, what does it say? Y-Men 1750, 1850. Yeah, that's good. So 1750 to 1850. All they're doing is encapsulating where we need to look. We'll just step out by 10. And then we'll just hit graph. And we can find that intersection. Second, trace, 5, enter, enter, enter. And it's 15.82. Or 15.83, I should say. So 15.83. 1820. Graph. Is 30.86. And then 1822. So let's go 1822. And this is to get these amounts out, right? So what does my compounding need to be? Let's go second, trace, and maybe it hit it since it told us to look out there. Yeah, okay. Let's just hit graph, one quit. Hit graph. We need to open up a window a little bit, so let's go, that's 52, let's go 152. Just graph. Let's see what it does. You know what? Let's go 400, because 365 days, right? So let's just hit graph. Let's see what it does. There we go. Now let's hit second, trace, 5, enter, enter, enter. Why is it not? Okay. Let's hit graph again. You know what? Let's go to table set. Let's go to auto. All right. And then let's graph. Oh, let's go to table. Let's go. I want to go to window. I want to start. No, set table set. Let's go 365, and then let's look at the table. All right. The reason why it's not doing it is this. It's approaching 822, but it'll never make it to 822. Okay, that's why we got that error that we got. It's just not going to intersect, right? So, to produce an A greater than 1822, N would have to be what? Well, it doesn't exist. We can't get it there. So I'm going to put D and E. Now, before we get into what's the calculator or what's the program going to want, let's just see. So let me count. So we got initial one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need to look at 10. Oh, they rounded. Yeah, they rounded up. Okay, they rounded up. So that's why. Okay, so they got 16 and they got 31 here. 553. No. We'll just give you what the answer should be. I'm saying this doesn't exist. They're saying it's 553. Let's just see. I don't think that's going to make it, but let's do 600. Graph. All right, so second trace, 5, enter, enter, enter. There you go. Just got to go out more enough. 552 point something, and they come up with 553. So, yeah, okay. Not a really good 553. All right, so just be noticeable that. Describe the line as effects. Well, it's not a straight line. They're saying it's AEG. I'm just gonna go ahead. That's not a straight line. That's what I don't understand. They're saying it's these. Select all the AEG right there. I don't necessarily agree with that. Because it's not a straight line. It has a horizontal asymptote. I mean, you can look at it. So there, we'll leave it at that. There's better problems to show compounding than this, and it's just, yeah, it's not a really good problem. All right, so here, there's that one. We're done with that one. All right, so expanding, when we have two things multiplied, we can say the log base bay of 5 plus, if they're stuck together, we can separate them by plus, right? T, and if they're done by division, then they separated by subtraction, right? T and 5. Okay, those are the properties of expanding, condensing logs there. Find the exact value for each. I'm going to show you the first one. Log of 12 of 144. X, some unknown, right? So I'm going to show you what's called a backwards C. I told you the base of the log and the base of the exponential are the same. Okay, so the base of the log, and it's called a backwards C, 12 raised to X is equal to 144, right? So if you look at that, that's b to the y equal to x. That's kind of how to do it, but I do it with a backwards c. Now, it doesn't give us the exact thing, but we're going to say 12 to the x is equal to 12 squared. See, I got my bases to be the same. I rewrote 144 as 12 squared, so therefore x has to be equal to 2. Now, we're going to show you how to do this on the calculator. Here's how you do it by hand. Let's get out of this and then quit. I got, let's see, 12 and 144. So it's the log of 144 divided by the log of 12. Ladies and gentlemen, that's 2. And then we can do another one, log base 3 of 243. So the log of 243 divided by the log of 3. We're doing change base, right? And that's 5. So change of base would be the log of 144 over the log of 12, right? Just so you know, log base b of a equals log of a over log of b. That's the change of base formula right there again. All right, so let's look at this. It's kind of, we just gave you log base b of x equal to y, right? And if we rewrote that into an exponential, it'd be by to the x, right? So, but if we were to do this, it would be the backwards c, right? Which would be log base 2, right? The base of the exponential and the base of the log are the same, of 1024 is equal to 10, right? So the y would be, looking at this, the y would be 10, the base would be 2, and the x would be 1024. Okay, so if you use this right here and the backwards c, you'll be okay. It's just converting a log to a base, or an exponential to a log, and a log to an exponential, not to a base. Sorry. All right, let's see how many more we have. Let's do this one, and then we'll be done, and that'll be part 3's video. So the base is 0.6, right? Of m is equal to 9.9, right? So we need to know what things are. So log base b of x equal to y. So we do backwards c, that's b to the y is equal to x, right? So the y is 9.9, right? The base is 0.6, and the x is m. There you go. So, ladies and gentlemen, yeah, I think this, yeah. Well, let's do this. Solve this. 6 to x is, okay. 6 to the z is equal to 3.5. The solution is given log base b of a. Okay, so we got to write this as a log base 6, right, of 3.5 equal to z, right? So let's do this. B to the x equals y. Well, better do it by what they've got, a and b. So let's do this. Let's do log base b of a equals to x. Well, not x. Let's just do a z. It's unknown. So if we do this and we do it by the backwards, b raised to the z is equal to a. So the a, well, the base would be 6. Right, the base of the log and the base exponential is the same. The a is 3.5, right? So if we do this, use trial and error to approximate the log to 1 decimal. We're not going to do that. We can do it in our calculators, log of 3.5 over the log of 6, right? We can do what's called a change of base. And when you do that, approximate to 1, log of 6, so 3.5 divided by the log of 6. Ladies and gentlemen, what did I just do? Oh, I know what I done. Duh. Log of 3.5, close parentheses, divided by log of 6, close parentheses, boom. All right, 0.699, which would be 0.7, right? There you go. Now let's just go ahead. They're wanting to know between what two integers this log of base 10 of 11.2 is. Well, we're going to say log of 11.2 over the log of 10, and we're going to give its decimal. We're not going to rewrite it. We're just going to solve it to the nearest 100. That's 2 decimal places, right? So we're going to do change of base. So log of 11.2 divided by the log of, let's see what it was, 10, right? Well, IB, that's a common log. I ain't got to do it real. All right, log of 10, 1.05. So the answer would be 1.05. So it'd be between 1 and 2. That'd be consecutive integers, right? So you could, because the base was 10, I could have just said strictly the log of 11.2. So I want to show you that real quick. Log of 11.2, because it was a base was 10, that means it's a common log, and the calculator set up for a common log. All right, so yeah, okay. These are all base 10s, right? So they're common logs. So we're going to evaluate them as this: 1.18, 11.8, and then, okay, we're going to look at all four of those, okay? And we're going to, so let's go to calculator. Let's clear this out. Let's clear this out. Make sure we got it. Yep. Okay, so log of 1.18, close parentheses, log of 11.8, close parentheses. So here's all your stuff, right? Log of 118, right? And then the log of that. So you can see that it's going up, increasing by 1 every time, even though the log of itself is going up by 10, the output's going up by 1, increased by 1. When the input, okay, it'd be A would be your answer. When the input of the common log is multiplied by 10, the output's increased by 1. And so that's what we saw. And here's your answers to all those, right? 0.0719, so 1.0719, pretty sure I got that, yeah. 2.0719, 3.0719. Okay, so that's what that's looking at. And then the last one is find the exact value. We can do a couple of things. We can, because this is an exponent, we can say 7 times the log of 4, base 4 raised to the 4. And we know that that's really 7 times 1 if we remember the properties. But we could say, because these bases are the same, the base and the of are the same, it's just the power, right? Because that's, if you use a property, you can see this. This right here becomes 1, right? 7 times 1. And if you look back on property, if the base and the of are the same, it's just the power. So there you go. So ladies and gentlemen, this concludes Chapter 5, Section 4.3 and 4.4, Section 3's video.